Welcome back to High Performance Computing, Lecture 6, Parallel Programming with OpenMP. That means essentially shared memory programming. We learned that in the first part of the lecture today. And we have seen it's quite different from the distributed memory paradigm that we have actually used a couple of last lectures, where it was always explicit message exchanges, send and receive, or we had the collectives, broadcast, reduce, etc. So in shared memory, we learned it's all about the shared address space and variables. That means we basically communicate essentially between different threads with this kind of shared address space. And we learned there CC NUMA and UMA, different architectures, so to speak, basically how the memory access is realized. But essentially you have this cache current links, then always this kind of shared address space you can assume while programming. However, another twist to this is what we learned. Usually people combine OpenMP with MPI, especially when you have large-scale HPC applications, because essentially where you were limited in OpenMP, you can imagine this will be the shared address space. So if there's not enough memory in the system anymore to get all your details of your simulation realized, then of course there's no point of staying inside the boundaries of the memory. However, we have seen with the speed of shared memory, it makes sense to really leverage this. And with the HBDB scan example, we have seen that even with the hybrid code, we scale much better. Of course, in the end, this reflects then the code that is more complex, because then you have suddenly basically message exchanges from MPI, and then in other parts, parallel regions of OpenMP with critical sections, single sections. We will learn basically all of these constructs now in the second part, but essentially I'm saying that it's getting more and more complex, and hence we have a complete next lecture then in lecture 7 that is talking about this hybrid programming with using OpenMP together with MPI. But then we also explored just a bit that, of course, this is also just the start. You have two more aspects that fall into it. Usually you would combine today accelerators. So accelerators are GPUs. We didn't talk too much about that yet. There will be a complete lecture on GPUs to understand this, why you basically have to load from the host memory things into the device memory, what the benefit, what is CUDA, and so forth. So the point is you would maybe combine MPI, OpenMP, and then the accelerator again. And there are some links between OpenMP and accelerators. We will also learn that there in these lectures. But it shows you another level of, let's say, complexity increase. And then what we also learned in OMS and PyComs and so on is then thinking about whole task dependencies. Of course, when you think about that using shared memory or using basically these systems then in hybrid computing, you can basically combine this with cloud. You go to a more coarse-grained perspective of your application problem that you maybe want to more or less semi-automatically want to parallelize, and some of them should be executed on shared memory because there's capacity. Then you want to have it on distributed memory or even in cloud computing in Amazon and so on. And this is another facet to it, to really look on the complete application workflow, dependencies, and this is quite substance that also would fill essentially a training of 3 or 5 days from morning till evening. Hence, take away the message that the first part of this lecture was really just giving you the overview of OpenMP, of shared memory and related work, so to speak, around it, and basically also some benefits like portability for sure. But let us now come to the idea of implementing OpenMP. So you're really using applications with OpenMP, and we will start very basic to think again in parallel. So what does that mean? A parallel OpenMP program. We learned already, instead of just processors, you have now basically, of course, still cores and processors, but basically they are different threads. And this MT always represents this master thread that we already have talked about in the first part of the lecture that is always existing. However, this master thread and the environment of OpenMP will then spawn different threads, which we call the team of threads here. And this needs to be not equal all the time. So it could be 5, could be 4, depending on the parallel region. And essentially, this means we would have always several parts of the application where we look what could we do in parallel. And this would be traditionally very much loops, additions, which are all good candidates for parallelization usually. And so we will learn in basically some of these basic building blocks today of how to do OpenMP. But as I said also, and repeatedly will say, if you really want to use OpenMP and really professionally, you need much more knowledge than in the OpenMP specification. We need there much more time. In this respect, you really need to do then another, let's say, build on top kind of tutorial or training. However, you get the basics here that enable you to fully understand OpenMP, the dependencies from C codes up to the idea of threads, and then also, of course, executing them on HPC systems. And here's a good, let's say, hello world example that we already know from many fields in computer science. Here is one for OpenMP, which shows essentially inherent scalability. So this is a fully valid OpenMP program, admittedly one of the smallest one that may exist, where you just have this Pragma statement, if you remember the OpenMP, very famous directive, and something you should know by heart, especially for the exam. So then whatever follows next will be parallelized, right, with different threads. But you see also clearly here, essentially we don't have anything like a rank from MPI or something like this, but we will see later we get something like thread IDs, where we maybe can then influence the execution flow. But right now in this hello world, we would say we want to parallelize this printout. However, we don't know how often. That means there's an environment variable here, this omp num threads, that is usually actually part of our job scripts that we use on the HPC machines. And this tells then the OpenMP environment, once you compiled and executed, that this should be executed 4 times. So this is not anymore like this idea that we have seen before. Again, we said it's a serial program, right? But here it starts a parallel region right away, depending on the team of threads that we configured, which is 4 in this example. So we have 1, 2, 3, 4 threads available. And when we now execute and compile this, we will see we have 4 times hello world. And essentially, the interesting thing is, as I said, master thread is always there, right? So it will be always doing parts of the job as well. So it's not just, let's say, the manager, but it's also make the hands dirty, so to speak, to really, execute parts of himself, and also the hello world. And basically then we'll fork a parallel region here, execute 4 times hello world on 4 threads, including himself as the master, and then we'll basically collapse this or basically join this together again of being thus the master thread. And once this is finished, this printf statement, the whole program is finished. So it's a very simple example of doing nothing more. However, important, as I said again, is to know really this compiler directives are key. As we see, it's not anymore this kind of send receive, which is here really the modus operandi. When we now want to program it, we need another header for C to really have the OpenMP library inside it. Remember OpenMPI, I do it sometimes also myself wrong. It is an implementation of MPI, right? It has nothing to do here with the OpenMP library. But it's, of course, an interesting exam question that every now and then is actually coming to the surface. So mark the difference between OpenMP and OpenMPI, which is an implementation of MPI and has essentially nothing to do with OpenMP here. However, the name is, of course, quite misleading every now and then. Basically, we have here 2 variables, number of threads. We have a thread ID, which is very positive news. That means we can differentiate threads. And with this, we can do, of course, much more than just printing out hello world. We can have an influence now by using the thread ID, essentially the program flow again, and say something like we did with rank equals 0. We can do here something like if the thread ID is 0. In other words, there's a kind of directive here or kind of a function that really gives us the thread number back, which is then essentially this unique thread ID we want to have, right? So, and of course, this is, depending on the number of threads that you have available. You also see the Pragma OMP parallel statement that you already know, but what we didn't know yet is this private TID. But it shows you already a little bit from the name where this is alluding to. Private means here it's for every thread, specific, unique, right? You have to think about that. Once we entering here, each thread will be working on this area here in the parallel region, not before. Before we have just the master thread. The master thread will spawn here, the different threads, depending on our, of course, environment variable. And then this would be executed, this Pragma with the brackets here, essentially number of times depending on the threads. And this is nice because then we can get the different thread IDs. And you see hello world from thread. So we expect that this would be now changing. If we have 4 threads, this should be probably 0, 1, 2, 3. But only number 0 in these threads will then do something special and we'll basically have another printout here and say number of threads. So we have just one output of this, while we expect 4 outputs of this, because only one of them will have the thread ID 0. I think you can really make the connection to MPI ranks equals 0, right? It's very similar. However, completely different from the terms of perspective that we are in MPI with the ranks, but here we add threads, right? The way how you work then with it and really use it in applications is similar like MPI as well. You would say you have your C program, you do your Pragma statements inside. Basically, here's a simplified version of it. As we say, hello from your main thread. As we said, this is a serial region. Then Pragma statement means we enter a parallel region. And depending on the number of the number of threads we basically configure, we then basically can get different types this executed here. The Pragma statement, when there are no brackets, is just basically then relevant for the function call we have below. Otherwise, you have to do really then the full brackets, right, that we have seen in the example before. This means a parallel region based on brackets, while this here is an example where the parallel region is really essentially just this one, because here we see also we are back from the main thread, right? Just once executed. You use your C compiler. There's no, let's say, specifics to it from a certain perspective. We still have our GCC, but we basically specify here F OpenMP to really indicate that this is now basically OpenMP code in it. It's still a valid C program, but of course augmented with this compiler directives. And the compiler then, as the name suggests, needs to know this and basically will then make this hello threads as an executable that is then really entering parallel computing. So serial code, which is automatically basically parallelized if you want, because here you see we don't really do anything in parallel. We just make a kind of small statement and say this should be parallel. And this is the beauty of basically OpenMP, something we really can, use here and quite makes sense to really have also in the practical lecture explored, where you see essentially it's not big differences. However, the work sharing then is of course different in MPI compared now to OpenMP here. We said the master thread is always there, so this is something what you know now by heart. I think that's easy to understand. You have this parallel region. So, but what you do in parallel regions can be different. We call that work sharing constructs. One idea is, of course, to have maybe a for loop, right? Let's say you summarize something over an array, multiply something. This is, of course, a very interesting idea to make options for parallelization when it's independently parallelizable or basically data parallel. We will come to that in a moment for examples. Another idea is to have certain sections that can run basically for different, let's say, areas in parallel based on different threads, where the team then has these different sections. Or, and this is of course a very specific item here, I will show you an example where you also can have just one, let's say, always parallel work here. But then with a single, you can just have one of these executing this, right? And these are different work sharing constructs. And when you go to the API specification, you find much more material. So this is just, let's say, a very rudimentary introduction of the major ones, so to speak. And we had this already a little bit in lecture 3 when we come back to this. We had here, let's say, pseudocode notation of an array that we want to multiply just by a constant. And immediately this should be, blinking in your eyes. As a parallelization guy, you would say, oh, wow, that's beautiful, because a constant is very easy to multiply with different parts of an array because it's independent of any other step we do in the for loop. Again, right? Again, to repeat, it's independent to multiply this constant basically with any other item here, right? I hope you see that. That's a very important thing, could be also an exam question. That's why this is kind of independent parallelization. And we, for instance, and this is just one example, we can cut essentially here the for loop in the middle, right? And then do the same thing. However, we do it, of course, on different processors with different threads. So you see here, there's thread 1 and the time are really used for that, right? So here we see now with the second time I have to actually executing this, I can do this basically in smaller time because I can now cut the array in half and then do the same thing. And it's completely valid because there's no dependency whatsoever to any other item, as you see with the index of E here. It's always just modifying the respective E. And this is, let's say, a beautiful example of really using parallel computing, and especially now for shared memory. That means it's very easy parallelizable to do so. Here's the example, perhaps a little bit more in a graphical fashion and in source code notation, which is really real. Of course, here now and then, this is simplified demo code still. You see what to do, maybe something with the vector elements here. But here's an example when you think about Pragma MP parallel for private E. You say E is something which every thread should have privately. Why? Because we basically have our own index now. We run over this array, right? If we have maybe 1,000 before from the input size, we don't know yet now, but essentially would say we maybe cut it now in half in 4 different threads. So we have 250, 250, 250, 250 on top of each other, right? So E would be 250, then 251, then basically going more, that the indexes together then will have covering all the 1,000. Each of them will only have the different 250 to really make them the 1,000 up. You also see the color encoding, which is again the notation we already had before, where we said there needs to be some shared material, but it's still nicely parallelizable from the index perspective, right? Which shows the color code. In order to get this fellow in X here, or the new X, right? I just need the old X and multiply it by the same index of the Y I have here, which is basically shared with everyone. And by doing so, it's very easy parallelizable, and I don't explicitly parallelize this here. As you see, it's still serial code, right? I allocate, of course, here the kind of memory space, but still all the parallelization is now done by the engine, which looks a little bit like here on the top. We will see private data from the threads will be, for instance, the E, the index I need for this different array. And the shared data that I would have here is then the X and Y that I can then use to basically, based on my private E, then to really do my computing in parts of the array, right? So every thread has only a part of the array, but will of course contribute then once this parallel region is over, that this array is fully, let's say, worked on by 4 different threads as an example here. And this is really a simple example. You can make it a bit more fine-tuning with different levels. And here's another example with private E, which we already learned, but we here have an OMP parallel shell about the chunk. Now the beauty here is a little bit that you have a so-called dynamic schedule in this. What do I mean by this? Is essentially, you see this a little bit here, that in static scheduling, you basically have a very homogeneous distribution of the tasks that are going to the different threads. But when you have, let's say, this dynamically chunk size here pieces, that means when one chunk is finished, essentially, then it dynamically gets assigned another chunk of the array and another and another. So it's a much more flexible way of doing so. However, of course, you have to also configure this. We have to look in this dynamic versus static and so on. It has to fit to your application. Here it's very straightforward. We just want to do, again, an independent addition here on the array based on the different indices. And based on the end, I really can crunch it down into, let's say, smaller parts. But then essentially this chunk size is a little bit like, getting always enough work for the threads in a very dynamic fashion once it's completed and can ensure to further work. Then coming back to the section example, if you remember, which was in the overview, it's a bit different idea how you do this. So basically here we have still, of course, a loop, but as you see, we don't do this with Pragma OMP parallel and then, the for and so forth. Here we have a so-called section, which is essentially leading to this idea that the sections are then basically used here in parallel to be executed. And it's really not iterative, right? Which means that the sections really are then again divided among the threads in the team, and the kind of independent sections are then nested in this kind of sections. You see OP sections, right? Again, sections here. This S is quite important in this part. And then you have Pragma OMP section, which is one of those, and the other section is doing this. You see here as an example, one section is doing the addition, another section is doing the multiplication, another one is maybe dividing. It's not shown here, but you see essentially here in the programming paradigm, multiplication, addition. Still, the beauty is it's completely independent, as you see here. And of course, a very nice idea how you can parallelize it. Now, comparing this a little bit, what's possible in terms of ways of manipulating variables, we have to also think about synchronization a little bit. And here's an idea of a shared variable called x. For instance, in the left part of this, where I say, this is of course an interesting point now when I specify that this should be executed many times depending on the number of threads. We have here a problem if you just execute this, because depending on which thread would have and read the variable x from the shared memory is like this literally, right? So you see this below. So of course, to work on this, essentially this different threads will work somewhere here on the chip and actually want to access a memory, but in the moment maybe one other one is writing while the other one is reading. And so we have so-called lost updates or race conditions of variable x. In order to avoid this, so that only one process at the time can do this, there's this critical statement. So here, this critical ensures with this region, there's only one thread at the time that can execute this. And immediately, basically the others are waiting, which is an important part of it. But while the other waiting, you have a good conclusion of this addition, and x is properly set in the memory again. Time for the other, thread to do the same, and it will read in this part the accurate value done by the thread before. We'll write it, we'll do the addition in the memory proper, and the next, and the next. I think you get the story, right? So essentially it says just one thread at the time. This could be limiting or maybe also overdoing it. Also think, of course, while other threads wait and do nothing is a very bad word in parallelization, which means idle time. We will come to this in a moment, but you can imagine that, of course, such constructs are something to review often. So do I really need this? Can I do a workaround around this? Or basically just be aware that this, of course, causes waiting time or more or less idle time for some processors, for some threads, sorry, when basically they want to execute this region. That's why maybe it's good also to think about the single But essentially, we still learn that the others don't really execute it. But at some point in time, it maybe also causes load imbalance. So there's not a perfect way around this. It's just the point that maybe this block, then really this input Y just needs to be executed once by one thread here. And this helps us with a single, Pragma OMP single directive. While of course, all of this is in parallel, remember, right? So this will be all many times executed, like here 4 times. This Pragma OMP single within this parallel region ensures that only one thread is actually doing this input here, while the others essentially again are idle. So again, warning lamps are already on, right? And we will come back to this warning signs, idle processors, when we look a little bit towards performance analysis in later lectures. So what are other constructs? OpenMP is very rich from the API, so we can find lots of tuning mechanisms, lots of ideas. When you think about that, okay, I have different parallel regions. This is a nice example of this specification. Every now and then, you maybe don't want to lose everything from the threads, right, that have been, working before. Let's assume we have 2 times 2 parallel regions. All of them have, let's say, 4 threads. You see this here as an example, thread 0, 1, 2, 3. And the source code is essentially here. And what you do is you essentially say then that you don't have a thread private here variable on this, which means an A and an X is only specified. That means a thread private variable could live beyond essentially this basically parallel regions, right? It's called persistence. That in other words, it means when we have our first, Pragma or MP parallel region finished, normally the values of A and X, of course, then should be disappearing. But as we specify them as thread private, this is something which then would be persistent to the second, which we have later. You see the dots are actually continued here in the second parallel region, where we then have, of course, access again to A and X. This is not the case, and that's why it's here in the example, for private variables. Thread private is different from private that you see here as B, right? So we specify here the parallel region within a parallel area, right? And so essentially then saying that here B is just a private variable, not the thread private. In other words, at the end of the Pragma section, this will be just basically, kind of stopped being existing. And when I want to use it then in the second parallel region again, you see here we use B again for the output, and it provides you here one explanation also in a more graphical perspective. Maybe here is B, and B you see is basically initialized properly in the first part here because we use it as a thread ID here. But in the second, when I'm entering this, there's no B anymore, right? So it's basically not initialized. So you see essentially B in the output is 0, 0, 0. And this is not the case for A and X. As you see here, A and X essentially remain the same. Of course, think about that when we do printouts, we have a race condition, so to speak, line by line to the output. Similar as we have seen with the MPI, the execution of this is never directly the same. You see thread 0 is here the first in both, but then it varies between thread 3 and thread 2. So this is typically normal, so don't worry about this. This is never really completely deterministic, depending on the execution time when basically one of the threads gets a hold on this printf environment, whether it's a screen, whether it's a file, whatever you program. However, important message is here the private thread variable, right? Dynamic threads are explicitly turned off here because they could help basically then with some workflow, but I think that's a bit too much here to say in this particular part of this lecture. You have, of course, more examples what you can use in terms of the API. They are powerful operators that we already know from MPI. basically the reduce operation, you know, it has a very special value in scientific communities because often these kind of reduce operations are really needed. We have seen all reduce in examples from MPI, and similar here, for instance, the reduce operation in OpenMP and also enables us to really specify different operators we want to use it, like plus or multiply. You see that here, the reduction basically over the result should be an addition. And then we basically fire this up in the kind of private variable E. So here again, we have the idea of parallelizing probably the loop. And by doing so, once this loop is finished, we also want to have a reduction over the result. And you see that here, that we basically put this in front of any brackets, not basically directly in front of the loop. That means it's only the loop that will be parallelized here with Pragma. And the interesting thing is, once this is happening, we already do directly result operation reduction of the final result. Now you see here, when the result is executed parts by part and then reused inside the right side, basically, of this equation, we can immediately see that, of course, here we will basically add up the result of this interesting multiplication here, thread by thread. But what we want to have is essentially, because we're not having any more an array or so where this is explicitly stored, it's just the same variable, right? Think about this again. So this is the same variable in the end. I want then the final result to be really the complete addition of the whole different arrays that have been parallelized. And in the end, it's basically then giving you this kind of vector dot product example, which in the end then gives you a scalar back. But this is done in the parallel fashion here, going, you know, in a static way. Static, remember, was a schedule. We're explicitly giving the work construct to the different threads inside this array, and then basically performing local results as part of the threads. But then the reduction enables us here to get then the global result automatically without any computing. This is done just by this reduction operation internally by the OpenMP environment. What are other applications? Now you immediately can think about, okay, we basically always have, again, the same vector additions. Of course, OpenMP can be also used for more advanced computing. Here you have a very famous example that we will come back to also in lecture 13. It's alluding to methods we call so-called repeated random sampling. In other words, Monte Carlo methods. Here it's statistics to the rescue, approximations to the rescue. We will use this in lecture 13, for instance, for protein folding to understand diseases like Alzheimer's in HPC. But here's a very simple example for OpenMP, how that could work. You see basically, essentially, when you have here the calculation of P, and what we can essentially basically do is we break this big problem of the calculation of P into one of 4 problems, which is essentially saying that we have a big circle, which is in blue, but we actually just look on 1/4 of it. And when we think about this area here of the shaded circle, this is something like the radius to the power of 2 divided by 4 times the fractions, essentially. And then the area of the square would be, of course, a complete radius to the power of 2. But the probability would be then, of course, to divide it again by 4. The way how you could understand it is, and you think about the dart game, right? And the probability, the chance of really hitting the circle, the shaded in blue, is then proportional to the ratio of the areas of the circle and the square. And this enables us a little bit to think about probability now. So it's a probabilistic approach. It's, of course, not concrete mathematics, hence we approximate P here. We don't really calculate explicitly P, but this is approximation, and then doing it, let's say, repeated times. That's why we talk about a repeated random sampling. Repeated times really brings us over time, then essentially with the ratio that I just discussed, with the proportional aspects, again, to the idea that actually P can be approximated using OpenMP. And something what I said was random sampling, we need random numbers for it. So how we use the random numbers is that when we specify the radius to be 1 here, we want to have random numbers, let's say between essentially 0 and 1, so that we hit always this box essentially with our dart and our random samples. And we can always basically identify those which are not on the circle by just, checking against the radius. That's pretty clear. That is the properties of a circle. So we can always say, essentially, when we have the normal distance here, which is actually the square root of x to the power of 2 plus y to the power of 2, which are the coordinates here of the dot that we get, or the dart location if you want. And when we have this distance, we can always say it's smaller than the radius, or it goes above the radius, which means bigger than 1. And then it would be not a hit, essentially in the blue region where all our points lie in darting. I hope that gets a bit more interesting to understand. First, real applications can be, used for it. Essentially, this is alluding then to this term. We say repeated because we do it incredibly often. It doesn't work if you just do it, let's say 10 times or 5 times usually. Here we're talking about the number of runs really from 10 up to 100 to 1,000 to 10,000, 100,000, millions. It depends, of course, again on your direct application problem. But you see that essentially here a little bit in this graphic, this repeated random sampling from all of these points, we can test against the, let's say, distance, and then can say it is a hit inside the circle or it's basically outside. Now, once we have done this kind of problem fraction, we can then, of course, suddenly think about, okay, we basically have then the ratio. All what's left is that we basically have then, of course, 4 times this hits within the radius, because we have these 4 areas, and the total divided by the total number of random numbers I really have, right? That is basically a little bit shown here. What you see here graphically to approximate P is then when you do it number on number of times, getting to a much closer estimate of P, right? But this means you need really it incredible often. By incredible often, this means and ensures that you really actually hit those areas that we want to need to hit in order to approximate the value of P, right? And you see it's pretty close already by 100,000, which is quite interesting because, of course, you can continue with HPC to 1 million and then maybe get more and more closer to this number. The OpenMP is essentially reflecting what I just said and summarizing it. You have essentially a Pragma OMP parallel. That's no surprise. We want to do this loop in parallel. We have essentially a kind of private E. That means we basically want to have our own index here. And as we understand now, essentially from these hits, they're completely independent, right? So again, all of these red and blues here you see in this visual explanation, which are essentially our darts we throw, they are completely independent from each other. We can throw as many as we want. There's no dependency, so it's very nicely parallelizable. All what counts is that this R nums should be increasingly very many. But the more you have here, of course, enables us to specify more threads, and with this actually can more parallelize. Of course, you ensure here with rand max something that we, of course, want only values between 0 and 1, right? When you basically do this, so that you not end up with something like essentially normalizing and so on, so that you're not something like very much off essentially the square here all the time. So this gives you a little bit more frame of really hitting, but we also said we can check a hit basically based on our radius definition, which you have, there's basically essentially defined here in mathematical terms, essentially saying then here this is smaller to 1, and basically here's a square root missing, but essentially saying that there we can actually have the hit plus plus, essentially saying how many times I hit the blue part. And then, as I said here in the yellow block, which is important to know, when I do this now 4 times the hit and divided by the overall number of runs, I have a very good estimate of the number of P. So this is something what we will also try out, and basically be careful every now and then, because I copy paste and do things from, let's say, many different sources. There could be a small typo, like here, for instance, a square root. But we come back in practical lecture 6.1 to this example, and then we have a view on this. Just to also link to other lectures which are coming up. So Jacobi 2D is something we already had, the heat dissipation. You remembered we had then the halo regions in MPI, because essentially to compute the next time step for the heat dissipation function, we need the time step before. And as long as this is in shared memory, we can do this in shared memory, of course, and we will have an example in lecture 7 about it. And of course, this would be very quick because you have, shared memory and very good performance. However, what we also learned is the bigger the space is, maybe this whole domain, and this, shadowed version here, this might be only your shared memory capacity. So you maybe have to do distributed memory because you are running out of shared memory. And this is something we will look at when we go to lecture 7, also in the hybrid examples, that this is a good example where when you want to have a bigger room simulated, then you maybe need to go distributed based on your shared memory code. So this is one example, also from the physics. And then let us compare a little bit, basically what we had with MPI, just to make a frame of reference, basically to MPI before we enter then the material of lecture 7 in one of the next lectures. But before that, we will have also OpenMP a little bit practically explored as practical lecture 6.1 coming up next time. So just summarizing a little bit what we learned, MPI, of course, we have unique IDs with MPI ranks. And we also learned with OpenMP, we have this thread numbers, and we have a very unique thread ID we could use. In other words, we can maybe do something like the master work approach, that only specific IDs of threads will do certain work items, like we have already understood in the MPI environment with ranks. So both of them are, in this sense, of course, very similar. They're both doing parallel computing. They have the way of having unique identification, which helps us also to adjust the parallel flow of this work. However, when you compare it now to MPI, we don't have really explicit communication. That means here, you remember on the left, send and receive, right? This is the explicit communication. I say I want to have this data block. I have to actually even reserve a buffer here, if you remember, on the receive part for data to be sent in the other memory space. So this is here, of course, completely different. In OpenMP, we have shared memory, so there is no buffer. There is no need to allocate buffer for sending because we have the same address space. I can just use this and read it out. However, we need synchronization because if many threads will modify the same variables, you see we get race conditions. We have other problems in terms of the correctness of the variables. And this, again, automatically leads us to some interesting problems that may occur that in a way then is also, again, similar like MPI. Remember when we had load imbalancing in MPI, right? We had this different ideas that, only one thread is maybe only one process in MPI is doing something if rank equals 0, and I have lots of things to do and all others keep waiting. Here it's about critical regions instead. So in OpenMP, you have also something which is similar like load balancing with MPI when you do barriers and so on. And here you have an idea that critical regions, of course, can be executed only by one thread at the time, which in other words means there's some extreme threads here that wait a long time to just enter this critical region to just continue what's afterwards. And this is idle time, of course, which is very bad in computing, if you remember, especially in parallel computing. The same is actually true here when you maybe have another barrier where there was a very fast, kind of computer, and he has to wait then for all the others here to finish. And this is all basically then partly idle times we have to think about and actually look at. Hence, there's of course then also performance tools, right? Performance analysis tools to the rescue. I will look in lecture 8 with you We don't do this now more in detail, but you can imagine there are different tools available to do so, to understand which is the situation in threats. Hence, we have a complete lecture about this. There's also more to be done with GPUs, as you can imagine. I left that also out today to really focus on OpenMP first, understanding master, fork, and the parallel regions before you join and come back to the master. In similar items, you can do this now with OpenAccelerator or OpenAC here, which is very similar to program actually, but instead, of course, it will be then sending the data not to the shared memory, main memory here, directly to the device memory instead. But these are things we will explore in lecture 9 together when we also know a bit more about GPUs. Just already to give you some pointer that, of course, OpenMP is very similar like OpenAC. You see it's modeled afterwards. That's why we basically will talk about it. And then when we come back to our parallel and scalable clustering as the last really big application example, I told you here, this is a good indicator. MPI on dataset 1 is essentially here having a tail off. And then when we see in hybrid fashion with dataset 1 with the same dataset, we continue here in a more or less close to linear scaling, which is of course very nice. Of course, in some point in time, it maybe also there's a tail off. But you see here already in this concrete thread, only with very limited core numbers, 512, that we already have here some difference. And the difference would be, of course, now getting the higher scale we come, probably more extreme. So it makes sense to combine it, but this source code here shows you that basically it's getting more complicated to combine these things. You have the threads, you have to specify the number of threads, you have to specify the number of tasks per node, things we also will learn more and more now when we have the practical lectures and more applications. And with this, you basically then have to specify how many ideas you really and tasks you really want to do there in the thread environment. But these are things that will materialize when we look a little bit more deeper in the practical lecture on these things. But this is a good example that it really makes sense to do so. However, it's of course much more complex to do this. And if you want to have the full source code, of course, it's open source here in this Bitbug repository of one of my former PhD students. And here's the description in the paper if you want. I want to close, however, the section with basically this kind of second part of the lecture with a small demonstration, again, why it's visible and how it also used in other application area, like in ray tracing, for instance. And this is a nice example because it shows you also the scalability, right? Adding more and more threads to the problem. So this is OpenMP, but here uses just one CPU. Ray tracing says frame per seconds, 7 frame per seconds. But still, let's say, a little bit, slow when you consider it like that. Now, basically, when you have now the parallelization with OpenMP, you can now think about that the same problem should be parallelized. You see here with 4 threads, and immediately it's getting much more quicker. And of course, the number of threads now here you see can be adjusted, can be more put basically to the threads and tasks, and with this get a much more speed up, a much more fluent way of how these planets or how this example is going to work. And this captures the essence of the scalability of this OpenMP program, right? Really dividing the parallel aspects, and with this being much more better and quicker. And here also leverage basically then the CPUs better and better. All right, I think that's pretty clear now. You can, of course, always increase Threats versus tasks. You have to be a bit careful on this, but you see it's getting more and more fluent here in this particular interesting example. Good, so that was all I really wanted to bring you today. We have the bibliography as usual, and basically continue now with one of the next lectures then with practical lecture 6.1, where we do some practical demonstration of OpenMP